Okay, you can see the title, and you can guess that there will be no equations. It is customary in these award talks to express appreciation for one's institutions, mentors, collaborators. I'm very honored by the award, and I thank very much the committee for it. I had plenty of opportunity. Without opportunity, it just doesn't happen. I've been to great places with great students and great collaborators, and like Stanford, I graduated from MIT, went to Stanford, University of Illinois, and ended up at MIT again. It's also customary in talks like this to chart one's intellectual roots and journey, and I will not depart from this tradition. So professors often give advice to PhD students, and a common set of advices, the canonical set perhaps, is first find a good and compatible advisor. Then take time to get a well-rounded education while you're in school, because you may not be able to do it later. That's the best time is at school. And make sure you get a lot of courses in math. You get some depth in math, because that's also the best time to learn math. Then start using your PhD thesis as the basis and the launching point for further research, at least for the first few years, maybe 5 years or so, and then gradually branch out into neighboring fields and network as you network within the profession. Now that's good advice, and I often give this advice to students. However, that's not how it worked for me at all. Let me take this one by one. Find a good and compatible advisor. Well, I have no advisor, essentially. There was, of course, a professor who signed my thesis, but that professor left MIT just a few months after I started working with him. In the meantime, I hardly had any contact with him. He went to a different university in a different part of the country, and I didn't see him or talk to him up until the day when I had my thesis defense. So I was entirely on my own. And okay, take necessary time to get a well-rounded education. Well, I just stayed for 2 years, my PhD study at MIT. I just did it quickly. And I took only 2 elementary math courses. I took linear algebra and modern algebra, and that was it. Then, okay, use your PhD as the base and focus for further research. My PhD thesis was on something called minimax control. You may view it also as a control of uncertain systems with set membership of the uncertainty. At that time, what was sort of at the very edge of research. It was an exotic field. You could call it a field. There were just a couple of pieces of work that had started in that direction. Nowadays, it's connected with robust optimization, robust control, has received a lot more attention. But then from MIT, I went to teach in a department that was the Department of Engineering Economic Systems. Now, these people were not interested at all in my thesis. And in fact, nobody was interested in my thesis for about 15 years. And I was quite upset by it, because I thought that I spent quite a bit of time on it, and here it was a useless subject, effort wasted. It turned out that 15 years later, 15, 20 years later, the subject became popular. My thesis did receive some attention, and today it's an active research field within the context of robust optimization and other fields in control, like modern predictive control and so on. Okay, gradually branch out into neighboring fields. Well, I changed my field right after my PhD, and I kept changing after that. The reason was that the Department of Stanford that I went to had an interest in both applications and theory, but the theory was in optimization, operations research, and also economics. And I knew nothing about operations research. I never took an optimization course while in school, and as far as economics was concerned, I was totally ignorant. And in order to survive and be able to talk to other people, I had to change my field, particularly since they were not interested at all in what I was interested in. So, okay, so my thesis was in control, Kalman filtering, and things like that. And then after I went to Stanford, I branched to optimization. Now, there I acquired mentors, but the mentors were not personal. They were through books. Actually, David Lowenberger had his office right next to mine, but he was also visiting places. I did get to talk to him once in a while, but I learned particularly from his books because I taught from them, and they were just outstanding books. In fact, I hardly know any better authors than David Lowenberger. I also learned from the convex analysis book of Terry Rockefeller, and I taught a course from his 1970 book. And also the books of Richard Bellman were very influential to me. I learned dynamic programming from them, and they were rich in both application and theory, and they were rich in ideas. I really liked Richard Bellman's books, and I taught a course in dynamic programming that launched me into that dynamic programming direction. Now, just as I was getting my footing in nonlinear programming, and I started understanding the subject, I moved into Illinois, into a control group back again, and then after wandering for a while, I got into a strange direction, okay? Stochastic control, but really esoteric mathematical questions, stochastic control. Measurability questions, I think Tamas mentioned them. Universal measurability, Borel spaces, really stuff that was out in left field for engineers. For mathematicians, there was David Blackwell and other great mathematicians who had worked in this field, but the field was under development. And there I worked with Stephen Shreve, my PhD student at that time. We worked together intensively for like 3 years, and we wrote a monograph. And just as this monograph was finished, I went back to MIT and started working on a technological field, data communications, data networks, a high-tech field. In fact, I was hired at MIT as an expert in data networks. I don't know where they got that, but that was the way it happened. But what was very nice then was that I met at MIT some great collaborators that with whom I worked for many, many years. And one of them was Bob Gallagher. He's a great guy. He was a major figure in information theory and communications. He knew enough about optimization, and I knew enough about his field that we could work together. And we worked together for like 10 years, and then we wrote a book, and then started branching out to other areas. Distributed computation, network optimization were connected with data communications, but had a more of an algorithmic flavor to them. And two of my very important collaborators are John Tsitsiklis, whose work was primarily in distributed computation, but also he knew a lot about network optimization, and Paul Zanko knew a lot about network optimization, but also was interested in distributed computation. I worked with both of them while they were students, and then they stayed on for a while. Well, John is still there. It's my next door neighbor. And so that lasted for a while. And from distributed computation, I focused back again to approximate dynamic programming, and I wrote a book with John Tsitsiklis on that. Around 1996, I ran out of directions to go. And I started working on all of these things. So that journey took 25 years, and during these 25 years, I often wonder if I'm doing something wrong. Why could I not stick into one area like other people did? But over time, I understood that somehow this was the natural thing for me to do. It worked well for me. Not for everyone, but it worked for me. And there were some major advantages to this mode of operating that I didn't appreciate in the beginning. By working in different fields, this cross-fertilization of ideas, you get perspective, you get ideas from one area to another, and that's good for research. The second thing is when you go into a new field, you come with a fresh mind. You're unencumbered by preconception or prior knowledge. You are free to develop new ideas in a more functional way than you would otherwise. And I'd like to close this talk around this theme of what it means, what it may mean to come fresh into a new field. And I'll talk about this auction algorithm, one of my favorite pieces of research. It's original form, it relates to the assignment problem, the classical linear assignment problem, where you have n persons that want to allocate among themselves n objects, and object j has a value, aij, for person I, and you'd like to find a one-to-one assignment so that the total value of the assignment is maximized. It's a classical problem and very fundamental problem, because any linear optimization problem can be mapped into the assignment problem. Now, at that time, my knowledge of network optimization, graph theory, and the like was extremely sketchy. I was just learning about it, reading books, reading about the primal simplex method, which seemed totally comprehensible to me, the dual simplex method. I could figure out that there were primal variables, which were flows, and there were dual variables, which were prices, and the two interacted through some kind of complementary slackness condition, and that condition was that, okay, so the flows here are the assignments. They can be 0 or 1, or in some other formulation, they can be fractional in between 0 and 1. It's a price for each object. And the complementary slackness condition says that in an optimal assignment, each person is assigned to a maximum profit object, an object that gives maximum value minus the price that he has to pay for it. So there is a market mechanism in this assignment problem along with the optimum solution. And then I was sort of, all of this were kind of hazy in my mind. And then one day I was at Illinois at that time, and there was a horrific thunderstorm and powering rain, and my house had a basement, and the basement started taking water, lots of water. And so I rushed down there with a bucket, and I was trying to empty out the water, and I had no books there. All I had was a bucket and paper and pencil. And I was sitting there for many hours, every 15 minutes going and emptying the bucket, and in between trying to figure out how to solve this assignment problem. But I had no books, and I had forgotten all this primal and dual stuff. All I could remember was a market mechanism. So I thought, well, perhaps the thing to do between them is just to bid for these objects by raising their prices. And if the prices of some objects get high enough, then they become unattractive for other bidders, and they go on and bid for other objects, and then eventually you get a growing assignment that can become a complete assignment at the end. So I looked at this idea, and then it struck me that it didn't work. It was just to get stuck, because it could happen that several persons, that some person would have equally attractive objects, and he would compete with other persons, and there would be more persons competing for less objects, and there was no way to get unstuck and to move some of the persons out of the assignment. So the idea came to me that you needed an increment for the bid. Whenever there were two equally valued objects or equal profit objects, you needed to apply a certain epsilon increment, like you do in real auctions. In real auctions, you have to outbid the other person by a certain amount. And that was kind of a simple idea, a little strange idea, and it worked. And the next day, I had the algorithm mapped out. And then I started working further, and there were some interesting things to understand about it. And it turns out that this algorithm is very different, entirely different from the classical simplex dual methods and so on. It is really a coordinate descent method, but in a strange way. Here's a picture that perhaps explains what's happening. You have a dual function that's defined over prices, P1, P2, and these are the level sets of this dual function. It's piecewise linear. And now, if you do coordinate descent means that you go from a certain point and raise the price of object 1. Going in the other direction means changing the price of the other object. So the auction algorithm was changing prices along coordinate directions. However, if you are at a corner like here, you can go in one direction for this object or in the other direction and get stuck. It's a situation where you have, okay, it's a classical situation with non-differential optimization. Why coordinate descent does not work in non-differential optimization. So now with the epsilon increment, one could go epsilon beyond the minimizing point and then epsilon beyond the minimizing point and overcome this impasse along the corners, and you could go forward to the, towards the optimal solution. Again, this seemed like a strange algorithm. It took, for quite a while, I did not publish it. However, it turned out, also through the work of others, that this idea led to excellent complexity algorithms. And in fact, the best complexity estimates for linear optimization, not only assignment, but also for transshipment problems, for transportation, so it's based on these auction ideas. And it also led to software that in part I wrote, in part with Bertsekas. And so that's what I mean by coming fresh into a new field. If I had books with me down in that basement, I would not have come up with this idea. So, okay, thank you very much.